Okay.
That's still reading.
We can probably just, or, oh, is it gonna, able to do it, or?
Yeah, I can do it, but it's still it's still reading the.
Oh,
USB,
okay,
so.
because otherwise we can plug in, plug that into here and then do the switch. This won't show up on Zoom, but,
Oh, yeah, okay.
so,
No, just yeah, just give me a moment.
okay.
It should read it. And it usually takes a little bit of time.
Some water.
Thank you.
You get free water if you show up there. That's your pay.
Yeah, okay.
Anyway,
Yep, I'm told. Yeah, sure.
you want to, we could just get started and then.
Yeah, sure, yeah.
Things down.
Yeah, just go ahead. Yeah.
Right, so Satish Sukumaran, he was my grad student a long time ago. 2002.
Yep, yeah, that's
So
when I
20
finished, yes.
some
21
odd
years, yeah.
Yeah, so. Anyway, so then he left here and we worked at Argonne for a while with the AGA, right?
Yep.
At IPNS and then was at
Mine.
Mainz, yeah. In the Polymer physics program there. And then Leeds with Reed and McLeish, and then Japan, yeah. So Yagamata University, kind of in the mountains.
Yamagata.
That's it.
Yeah.
And then anyway, he's going to talk about. He's been doing simulations. He's worked with all the top simulation people. So he's going to talk about chain entanglements and Chalmers, which is one of the main things that he's been doing for a while. So anyway.
Okay.
He's got a video, so he's kind of putting it onto the
All right, yeah, that would.
onto the flash drive. We could have done before, but
Okay.
it's already open.
Okay, so yep, it's there. Let me just see if it runs. Yep. Okay, doesn't seem to work. So
Oh, it's not playing?
yeah,
All right, then we can just plug in the VPN into your computer.
yeah, none of them seem to work. So I don't know.
All right.
No, it's all
We
right.
can plug it into the,
Yeah, HDMI.
yeah, and then when you want to do it, just well, you just click this button, you do it. So you'll just go from PC to that thing.
Oh, I see.
That should just do it. Yeah, so that's just projecting it.
Oh, wow. Okay.
Right.
Yeah, I probably have to.
The Zoom can see it too, anyways, camera there.
Oh, I see. Okay. Yeah,
So-
let's forget about this. Which is it? So this one.
All right, so what do you take off?
Okay. Wait. Okay. All right. Thank you all very much. I mean, as Greg already mentioned, so this topic, this talk will be about chain entanglements. I'll first introduce a way how you can visualize entanglements in a polymer melt, and then how well it works, and then finally it's a move on to our more recent work on binary blends. Okay, so all of this is on molecular simulations. Okay, so and before I start, please feel free to ask me questions even during the talk. Right, it's not an issue. Okay, let's go on. Okay, so first, let me give you a brief intro about what is the phenomena we're interested in understanding. And I'm sure all of you have seen yeah, such a nasty plot. Is that like a pointer? Or just use the mouse, I guess. Yeah. Okay. This is what is known as the storage modulus, G prime, and the loss modulus, G double prime. And the y-axis is over a couple of decades in magnitude, but please notice the x-axis, and that's over like 11 orders of magnitude, okay, in frequency. And of course, no single instrument or even several instruments will give you this data. I mean, such data is obtained by what's known as time temperature superposition, where you do simple shear rheology. So you take a cone and plate rheometer or a parallel plate, and then what you do is put the sample between two plates, and then you apply an oscillatory shear, and then watch the response. Okay, so you apply a deformation, and when you watch the response, what happens is the response, which is the stress, typically lags behind the deformation oscillation. Okay. Since it lags behind, you can have you definitely have an amplitude of the stress response, and you have a phase lag. And if you have an amplitude and a phase lag, of course, you can express it in the complex plane, and by writing it as the real part and the imaginary part, which is which are nothing but the G prime. The G prime is the in phase component. Which means that it stores the elastic energy, and then the G double prime is the out of phase component, which means it's 90 degrees off. Right, so that tells you how much loss happens, okay, because it's a viscoelastic material, right? And then for typical polymer melts, this data is actually for polyisoprene, and the data is for several molecular weights. You start with a very, very low molecular weight, which is like 2K, and then you gradually increase the molecular weight. What I want you to focus on is that as you increase the molecular weight, beyond a certain molecular weight, it appears as if the polymer melt exhibits no relaxation at all. Okay, the G prime and the G prime remains roughly constant over, let's say, 3 or 4 orders of magnitude in frequency. Okay, so it's as if it's not relaxing at all. And what doesn't relax is a rubber. Okay, so people, when they saw that, they thought, okay, there must be something like temporary crosslinks in a melt, and then we'll just call them as entanglements. Okay, that's where the idea of entanglements comes from. And this thing, this particular value is unique to a polymer melt. So like different polymers have different plateau moduli. And by using rubber elasticity theory, you can convert it to a molecular weight between the so-called temporary crosslinks. Please remember, these crosslinks are all in our mind, okay? Nobody has observed these crosslinks. But this phenomenon looks very similar to rubber. So let's think that there are some crosslinks in there, and that's how we are going to model it. All right, that's the idea, which also means that you can think about a molecular weight between these temporary crosslinks, which is known as the entanglement molecular weight. Okay, so to make this simpler, I actually did a schematic where instead of frequency, we can do it as time. So at very short time, we have the glassy response. So even like polymeric liquids at very, very short times behave like a glass. Okay, so your modulus can be of the order 10 to the 9 to 10 to the 11 pascals. And then at longer times, it slowly start relaxing. Okay, this is the polymeric part, which is like typically modeled using, let's say, the Rouse model, or in a solution. You can use the Zim model, etc., if it's a dilute solution. And then there is this flat part, where it looks like the relaxation has been arrested. And this part is what we are going to be interested in. So this plateau modulus is inversely proportional to a degree of polymerization between the crosslinks, or the molecular weight between crosslinks, within quotes, okay? This is the number I'm going to be interested in. And this number of monomers between entanglements is highly polymer specific. And there has been no a priori theory to understand this. Okay, And why is that important? All right. The reason that number is important is that if you know this number, you can use it as an input into the so-called tube model of Dow and Edwards. Okay, what the model does is, we have a complicated polymer melt. Let's focus on one particular chain. Okay, this is a very, very difficult so-called many-body problem to solve. So we are just going to assume that this particular chain can be modeled as being enclosed within a tube, which means it can move along the axis of the tube, but cannot go very far perpendicular to this axis. And the degree of constraint is referred to as the tube diameter. Okay, so this tube diameter needs to be input into the theory. It's not an output of the theory. Okay, it's an input parameter. And it turns out that that parameter is of course related to this molecular weight between crosslinks that I introduced earlier. Okay, that's why this parameter is interesting. And then experimentally, they found that this molecular weight between crosslinks divided by the polymer melt density actually exhibits a pattern. Okay, where here the x-axis is the so-called packing length. I'll introduce this packing length in more detail a little bit later. But the point is, what had earlier appeared pretty random, actually, once you come up with the appropriate length scale, there does seem to be a pattern, and the slope is something close to 3. Okay. One of our goals was to understand this. Where does this come about? All right. So this is kind of our motivation. Okay. So to put it very, very simply, how can we go from a complicated structure like this? Here I've actually indicated a network, but at the level we are thinking about, a network and the melt are very, very similar. Okay. So you can think of the entanglements as just temporary crosslinks. So that's not an issue. So we want to go from here to the so-called tube model. Okay, we want to get the parameters of the tube model. So the so-called traditional or the mathematical way of doing it is using so-called topological invariance. That's really, really hard and nasty, and it has not been very successful. So we completely sidestepped that. And then we decided to take a more physical approach, which is already used in the literature. Okay, so the idea is, you have a chain, and then the constraints of the other chain are represented by these dots. And the basic point is that when a polymer chain tries to move, right, it cannot cross any of those constraints. Okay, because two chains cannot cut through each other, but they can slide past each other. So that is the constraint which is behind the so-called entanglements, or the phenomena that result from entanglements, which is just a physical thing. If you have two wires, they cannot, you can't just randomly put them through each other, right? There's a physical constraint. And that is all entanglement phenomena stem from. Okay. So the basic idea is, so the chain cannot cross this, basically. Okay, this is a 2D projection, so you have to imagine it in 3 dimensions. But what you can do is, you can kind of remove some of the slack, and then come up with a much tighter version of this contour of the chain itself. Okay, so, and when you try to do that, you cannot cross any of these constraints. So you can go from the red to the blue without violating the constraints. And this blue is what's known as the primitive path. So this idea already existed in the literature, and the concept was that this primitive path is nothing but the axis of the tube itself. Okay, so if you can somehow obtain this, not just for one chain, but for all the chains in the melt simultaneously, and so that can give you a way to link the structure of the melt itself to the tube. Okay, so this is the idea we were going to build on. And what we did was, so I'll just skip this. This is not that important. This is the model details. Okay, so what we wanted to do on the computer was this. So let's take a chain, and then I've indicated a couple of constraints due to the presence of the other chain. So what we did was we fixed the ends of the chain in space, and then you can basically turn off the repulsive interaction between the neighboring beads, because it's a computer, right? You have complete control over the potentials. And when you do that, what happens is that the chain starts shrinking, but you retain the repulsive interactions between the chain under consideration and the other chain, so that they cannot cross over. Right. So yeah, what happens is all the slack is removed, and you have basically straight segments which connect the two ends of the chain. And then we claim that this is the primitive part we are interested in, and that's what we are going to use to come up with the statistics of the tube itself. Okay, so this is the fundamental idea behind this work. And then okay, this is where I wanted to show you some videos. Let me see if I can. This doesn't work, right? So I have to switch this to this. Oh, yeah. Okay. Which one? This one?
Yeah.
Oh. Okay. Yeah, let me see if I can get this. Okay, so basically what I have here is a visualization of a polymer melt, simple bead spring model of a polymer melt. Okay, so the different colors indicate the different chains, right? Yeah, nothing fancy. Okay, so and then step by step, I'll take you through the procedure I just introduced to you just a little while earlier. Okay, so that's not that interesting. So let me go to the next one. Sorry, I'm trying to play with two screens and it's a little bit complicated. Okay, so basically what I'm going to do now is focus on one chain. And when I do that, that's really small. Okay, so basically you can see that the slack is getting removed. And then essentially I'm only doing it for one chain, right? So it should become like a straight line because there are no constraints. And that's what happens. Okay, now let's do something more interesting. Just 1 second, if I can get the video. Okay, now what I'm going to show you is the same thing for two chains, okay, just two chains. And then once again, you see that all the slack is getting removed, and then there will be one kink where the two chains hit each other. Okay, so now the point is, for these two chains, you see that the length of the primitive path has become a little bit longer than the straight line which was there in the first case. Okay, so the next step is I'm going to do this for all the chains in the system, okay, simultaneously. Yeah, basically I've highlighted one chain in yellow in between, but that's not the most crucial part. Okay, so basically, yeah, okay, that disappeared too fast. Let me try that again. Okay, So here what we have is, if we focus on one chain, we can see like all the other chains that are hooked onto this particular chain, okay? So this gives you a way to visualize what are all the other chains that are entangled to your given chain. And to the best of my knowledge, this was the first time this was this has ever been done using simulations. Of course, it's not possible by experiments at all, okay, directly, right? So we have this so-called primitive path meshwork, and as you can see, right, there are kinks here too. And that's because there are other chains which are hooking onto those chains, okay? I only focused on all the chains that are connected to our chain of interest in yellow, all right? So now what we can do is we have this configuration, so we can do statistics on these, and from the statistics you can get the tube diameter, etc., and you can use it as your input for your melt. Okay, all right. I think that should do it. So let me head back to PC. Oh, I see. Yeah, because it says on projector. So.
Is it shown on the screen?
Yeah.
Okay. Just showed up.
Oh, okay. All right. It did. Okay. Right. We have obtained our primitive path mesh, and let's see what we can do with this. Okay. So basically, let me I will show you some examples. It's a little bit faint here, but I mean, here we have a comparatively stiffer chain versus a flexible chain. So like, these are just two different melts where the only difference is the chain stiffness between the two chains. Okay. And then if we see like how their primitive path meshwork looks like, it's actually like for the stiffer chain, it looks to be much more dense when compared to the flexible chain, right? So like this is something we can what this means is that because like this is significantly less dense, it means that the it means that the number of monomers between entanglements, or the entanglement molecular weight, is significantly larger for a flexible chain as compared to a stiffer chain. This might be counterintuitive, okay, because you would think that a flexible chain can knot upon itself easier. Okay, so you think that that should be more easily entangled, I mean, when compared to a stiffer chain. But the important point here is that entanglements are constraints essentially because of the presence of the other chains in the system. And if you have stiffer chains in a local volume, there are more chains which have to thread through the local volume to make the melt density. And that is why the stiffer chains are more entangled than the flexible chains. So please remember, the entanglements is not because of self-knotting, it's because of inter-chain constraints. Okay, so this is something that becomes very obvious once we visualize it in terms of the primitive path. And experimentally, this agrees very well with experimental results. But please also remember, this does not extend all the way to fully semi-flexible chains, like, for example, DNA or actin. Okay, there we'll enter into a completely different regime. So this is for flexible chains, but whose Kuhn lengths are a little bit different. Okay, like, for example, polystyrene versus polybutadiene, etc. Right. So like that is this is something I mean we could do very easily with our simulations. Okay. Yeah. Sure.
So in your simulations, the angle in chain are over 50.
Yes. So I'm just looking at one configuration. See, first I equilibrate the melt. Okay, so it is in thermal equilibrium, and then I take one configuration. And to do the primitive path analysis, I fix the ends. Right. So like this is a completely artificial construct. So there's nothing natural about it in terms of molecular dynamics. This is something we do to visualize the primitive path. I mean, to obtain the primitive path meshwork. Right. And then how we analyze it is we say that the tube diameter is nothing but the Kuhn length of the so-called primitive path I showed you earlier, okay? Because there were straight segments with kinks. So of course we can like define a Kuhn length, and the Kuhn length is nothing but the mean square end-to-end distance of the primitive path divided by the contour length of the primitive path. Okay. And once we have that, we can directly plug this into the classical equation for rubber elasticity theory, but slightly modified because it's these entanglements can actually slide, right? If you have a proper cross-link, the two chains are like connected is at that point, but entanglements you can actually slide, and that's where this 4/5 comes from to account for what are known as longitudinal relaxations, but that's not that important. All right, so we started from a static configuration, and then we obtained a physical property without any fitting parameters, basically, right? So now we have to see like whether it agrees with experiments or not. And that's what we did, okay? And of course, to compare it with experiments, you have to like non-dimensionalize it. Okay, before that, okay, I didn't define the packing like this, sorry. That probably comes a bit later. So we had to non-dimensionalize it, and the y-axis is the y-axis is the non-dimensionalized plateau modulus, which we calculated here, okay? And we non-dimensionalized it using the Kuhn length cubed. Because plateau modulus, right, is nothing but the units of the modulus is basically energy per unit volume, right? So like one natural energy per unit volume is kBT divided by the Kuhn length cubed. All right, so we use that modulus scale to like non-dimensionalize the y-axis. And similarly, x-axis, we take the ratio of the Kuhn length to the so-called packing length, which I have not defined yet. But it's something which we can calculate from the structure of the melt itself. Okay, it's a function of the mean square end-to-end distance and the density, etc. Okay, so here I have data from several kinds of polymers, which are actually from a series of papers by Fetters and co-workers. Okay, so like those are all these different colored pluses, and then the crosses are for two different solutions. And this is the equation that seems to fit everything. Okay, and these dark squares and the dark circle and the diamond are values obtained using the primitive path analysis I just showed you. And these hollow square and diamond are by actually deforming a melt in simulations and obtaining the plateau modulus by watching the relaxation. Right. So the first point is that this primitive path analysis agrees with direct calculation rather well. And then it also looks like it agrees with the whole slew of experimental data. Right, so like this, this was our confirmation that this method perhaps has some meaning, right? Basically in simulations, the good thing is you can do anything, and the bad thing is you can do anything. Okay, so you have to make sure that what you do makes sense. Okay, so you have to keep close contact with experiments or like fundamental understanding, etc. Okay, so then what we wanted to do was, so like we want to, basically, right, we wanted to extend this to the to blends. So like we had like two different chains with like very different entanglement molecular weight, right? And since we had a way of looking at entanglements directly, we wanted to see what we can do if we do for blends. And then, okay, I'll skip all of this calculation. But the basic point is that for a blend, by thinking about some of the ideas introduced for a polymer melt itself, and then extending it to the case of, straightforward extension to the case of a blend, we can see that the tube diameter in a blend should be the harmonic average of the tube diameters of the two individual components, which go into the blend, okay? And unfortunately, some recent experiments completely disagree with the expectation. Okay, so this like dashed line here correspond to the equation I showed you here. However, experiments are like significantly deviate from this. Please remember, this is log scale. Okay, so this deviation is rather significant. Right. So to to actually explain this, the authors of this, the authors in this paper, they actually introduced a different mixing rule. Okay, so this is what we expect from our classical understanding of entanglements. And however, experiment seems to suggest that like this mixing rule works better. Okay, so like here, this is just the volume fraction of the two components and the tube diameter of the two components. However, this is actually the number fraction of Kuhn segments present in the system for each component, right? So it's like it was completely out of left field. So that we don't have any understanding of why it should be so at all. Right, so we wanted to see if we could use simulations to shed any light on this at all. Okay, so just to remind you, the classical expectation deviates significantly from experiment on polyisoprene and polytertiary butyl styrene. These experiments are quite challenging. And they're rather difficult to do, but this is from Hiroshi Watanabe's group in Kyoto University. They did these experiments over several years, and finally they show that it doesn't work, basically. Okay, Greg, how much time do I have? 20 minutes. Okay, about 20 minutes. All right, I think that should be plenty of time. Okay. So what we wanted to do was the experiments we wanted to understand are blends of polyisoprene and polytertiary butyl styrene. Okay, so this is a schematic. And what I've identified here are what we thought of were the important factors that one needs to consider to understand this blend. All right, the first is like polyisoprene is a rather a flexible polymer, and then its Kuhn length is also not that high. So the monomers are also tiny. Okay, there's basically the backbone. There are not significant side chains in the for polyisoprene, and then its tube diameter is rather small comparatively. Its TG is extremely low. And the thing is, to contrast that with polytertiary butyl styrene, this is just a polystyrene with a tertiary butyl group, bulky side group hanging from it. Okay, so its TG is actually higher than polystyrene itself, and its tube diameter is also roughly double that of polyisoprene. So this is a crucial point. I mean, whenever you want to think about mixing rules for blends, you have to make sure that your starting components have tube diameters that are sufficiently different if you want to distinguish between the different mixing rules. And this was a problem in the classical literature because the tube diameters were actually quite close. So basically any mixing rule will look like it works, okay? So like this one, it's like a factor of 2 difference was there. So like you could clearly distinguish between the mixing rules. And the experimental problem is typically if the mixing rules, if the tube diameters are too wide, those polymers typically don't form a one-phase blend. I mean, they phase separate. So like this is actually quite a special system where they found that all the constraints were satisfied so that they could explore this in detail. Okay. So like we have to understand the effect of stiffness and the effect of monomer size, etc. So in simulations, we can like isolate the effect of each of them, right? So that's what we did. We first looked at blends of comparatively stiffer chains to flexible chains. Yeah, these things mix without any problem at all. Okay, so what we did is like to a simple bead spring chain, we introduced an additional bending potential, and by making this low energy configuration, if you set it to 0 degrees, then the chain prefers to go straight. Okay, which means it's a comparatively stiffer chain. Whereas if you make it 90 degrees, then it'll be like quite wiggly. So it'll be that's what I'm going to refer to as a flexible chain. And then we blend these two chains at different volume fractions or blend ratios. Okay, we also did another blend where this minimum angle was at 20 degrees, and then we compared it with a 70 degree. And okay, all right. So the rest of simulation details, and then what we did was we did primitive path analysis on this blend, and then we determined this like so-called entanglement degree of polymerization directly from the primitive path for each of the components, because we basically roughly know the distance between the kinks, etc. So we can count the number of monomers and then just average it. Okay. So like this is as expected. I mean, I already briefly indicated to you the flexible chain has a higher entanglement molecular weight. And then when you blend it, that gradually decreases. So like this is the flexible chain entanglement molecular weight. Whereas for the stiff chain, it increases, but not very significantly. All right, so like this like follows expectation. But what's interesting is that if you take this entanglement degree of polymerization and convert it to a tube diameter, both of the components show the same tube diameter in a blend, which means there is only one tube diameter in a blend. Okay, you don't have a tube diameter for each component. And the way to intuitively visualize is so you have a very dense polymeric system. And then you can think of it as forming like a mesh network. And in that network, you can introduce a polymer, and like that's what is going to create the tube for that polymer. Okay, so irrespective of the two components, you should be seeing the same local environment. So your tube will be very, very similar. Okay, that's the intuitive way to understand this. All right, so we basically that also seems to work for both the components. All right, so this is only the flexible chain for the two cases, and then these are the two stiff chains. But for the three blends, you can see that both of them have tube diameters that are very, very close. Okay, so of course, right, we wanted to understand the mixing rules. So we compared the two mixing rules, and it turns out that for these kind of blends, the so-called classical mixing rule, which is this works, this doesn't. Okay, that fails miserably. Right, that's what is indicated here. Which means we still don't understand why experiments work the way they do. Okay, it's not the difference in stiffness which is giving rise to the so-called anomalous mixing rule. Okay, so the next thing we wanted to do was this is just a summary of that. Let me go ahead and leave some time for questions. So the next thing we wanted to see was what about the difference in monomer size? Okay, so like what effect does it have? And then, basically what we did was we created two sets of chains, one with, let's say size 1, and then the other one, basically a monomer was just twice the size, right? And what happens when you do this is that the two systems phase separate right away. Okay, so like you have to play with the interactions a little, play with the interactions a little bit to get it to actually mix, but like it was possible. It's not So if anybody is interested in those details, like, yeah, please talk to me after the talk. I can give you those details. And like here, what happens is that you have the entanglement degree of polymerization for the small bead chains. That's indicated here, and for the large bead chains, okay, that's indicated here. So similar to what we did earlier, let's convert it to the tube diameter. So now, once again, even for these blends, there is only one tube diameter in the blend. Okay. Please remember, we calculated the tube diameter for each individual component from its own primitive path. And from that, we calculated the tube diameter, and it turned out to be the same. Okay, so like this is a result of the simulation. It's not something we are putting in by hand. Okay, so once again, let's compare the two mixing rules. And like, this is the so-called classical mixing rule. But now the mixing rule proposed by the people from Kyoto, which agrees with experiments, seems to work for our case too. Okay. So from this, of course, the first, so from this, the first suggestion or hint, a hint of what's going on in experiments is that monomer size difference seems to matter. Okay, it's not the stiffness which leads to these anomalous mixing, but the so-called monomer size difference. But how should we think about it? What is the what is the monomer size difference actually doing? Okay, so this indicates the local structure of the melt. Like this is this what's called the interchain pair correlation function. Okay, so what this indicates is that if you start from a monomer belonging to a particular chain and go in any direction, what is the probability of finding a chain belonging to the other component? Okay, basically those are known as like LS. So for the large monomer chain and the small monomer chain, or if you want to do it for the same type of chain, okay, the large monomer chain hitting another large monomer chain, that's indicated as LL, and similarly for SS. Okay, the crucial point here is that when you start with the large monomer chain, I mean, you have to go a certain distance, and there is some probability of hitting another chain with large monomers. Okay, similarly, when you start with a small monomer chain, there is some probability of hitting another chain with small monomers. But importantly, when you start with either a large monomer chain or a small monomer chain, you have a comparatively higher probability of hitting a chain belonging to the other component. This means that large monomers are preferentially surrounded by the smaller monomers, and smaller monomers significantly outnumber the large monomers. Okay, so like each large monomer is twice its size, which means it's 8 times its volume. And if you keep volume fraction 50-50, the number of chains belonging to the large monomers is going to be significantly smaller, at least by a factor of 8, right? So basically, this says that the mixing essentially is not uniform at all. It's not random mixing. It's highly non-uniform, and that is why these blends are actually miscible. Okay, and this the large monomers being surrounded by the small monomers may be the reason behind this anomalous mixing rule. Okay, it's not we think it comes from a non-uniform mixing, the non-uniform mixing in the blend itself. I think I'm probably over time. Okay, I think I'll just stop here, and I'll just be happy to take questions. So the lesson is basically like using simulations, we can look at entanglements, and then we can also identify things which cannot be easily distinguished in experiments. Okay, so thank you all very much for your attention.
Question. Straighten the chain out, and make the two. Then you go back and use the Gaussian, the random motion to get the modulus.
Yes.
The first part.
Yeah. That is just,
So
yeah.
that's- I mean, once you straighten it out, it's not Gaussian anymore.
Yeah. So
You're applying like a random model to the modulus.
no, you have to be careful here. Okay, yeah, this part, right?
Yeah.
See, because I fixed the ends, the mean square end-to-end distance of the chain doesn't change before or after this like shrinking process. Okay, yeah, this part like is still the same mean square end-to-end distance in the melt, right? Yeah, this is just a way for us to get this primitive path network so that we can like plug in this value LPP, which we calculate from this configuration. That is an artificial construction. We are not doing any real measurements from that. All we are doing is getting this LPP. Okay, so like once we like do that, we can get this Kuhn length of the primitive path. And this equation is directly from classical rubber elasticity or classical entanglement dynamics, right?
For a random thermally moving chain, right?
Yes. So like I'm saying that for a thermally moving chain.
But once you make it into a stiff path, it's not thermally moving.
Yes, but like I'm just using this ruse to calculate this APP. That is all. I'm I'm not measuring the modulus of this thing. I'm claiming by using this whatever technique or procedure or method, I can get hold of this. I can get hold of this value. I mean, which I can plug it into the classical equation from Dau-Edwards theory itself, because like this equation is just Dau-Edwards theory. Okay, but unfortunately, Dau-Edwards theory does not know this. So I'm just saying by playing this trick or whatever, I can obtain this. And the proof of the pudding was in the next page.
Yeah, I can see that it works.
Yeah, that's it.
No question about that.
Yes. So like, I'm not measuring it at all. See, I'm not measuring the modulus from this.
That it works doesn't mean it's right,
Yes, but the fact that it works is better than the fact that it doesn't work, right?
That's true.
Yeah. So see, like all models are wrong, but some models are useful.
Okay.
Right. So like that's what I'm going with here. See, that's not my line. That's of course George Box's line. I mean, so like all models, we're just trying to like capture aspects of reality. And we have to make sure they work, right? If they are useful or not. And we think this is useful. Okay.
So once you go to this primitive path.
Yeah.
But you're saying the molecular weight between the ends is still the same? No,
Yeah, of course, right?
So,
See, like,
so if you put in a bead the size of the path, they like overlap with each other.
yes. That's
So
just a technique to get this primitive path, because we need
to show that on your slides, like when you get to the larger, so they.
This one?
Well, yeah, that would be okay.
Yeah.
See the
Okay.
top and bottom. So
Yeah.
they overlap, right?
Yes. They will significantly overlap.
So what's, I mean, is that real? You're saying that's not real? Or?
See, like, ultimately what I'm interested in is the length of this thing, right? So that's what I'm indicating as LPP. So how does it matter if the beads overlap or not?
I don't know, I'm asking that.
Okay.
Are they not beads, they're not symmetric anymore, they're like discs? Or what?
No, there's still beads which significantly overlap. But I think that's just geometrical artifact of starting with the bead spring model. For instance, you can like make it into a thin line. It absolutely doesn't matter. You just have to make sure that the lines don't cross. That is all. That's where the physics lies in this. Okay, all of the rest are just like minor details.
That's good. So you fix the tube diameter for the two diameter is the same for the large
Yes,
small
yes,
in the last part, right?
Yep,
And
yep,
same
yep.
For the stiff and that's the,
yes,
so the tube diameter can be the same, but the consequence of that can be different. Like they have a big.
yes,
tube in
that's the
in
point.
tube. So say the tube is the same size as the largest bead, it would be stuck, right? But the little bead can move a bit laterally.
Yes,
And the stiff one, and same with the stiff and the flexible, even though it's the same tube, the chains dynamically are behaving totally different.
yes, very, very different. I have data like on dynamics, which is very interesting, but I figured I wouldn't have enough time to go through it, and I was right. So I didn't include it. If you say, in fact, right, the blends with different stiffnesses behave as expected, which means when you blend it, the fast component becomes slower and the slow component becomes faster. Okay, that's what you would expect like, when you blend them together, right? But like, when the size a size ratio is 1:2, the fast component becomes even faster and the slow component becomes even slower.
Oh, so you see that?
Yes,
Okay.
yes, we do see that.
So this harmonic rule is for rates, right? That's an average for rates. Like if you went two different speeds.
Yeah, exactly.
You get the average. Speed
Yes.
from that.
Yep.
And the other rule isn't for rate.
No, it's not for race. We actually don't know where the other rule comes from. And I've talked to the authors. Yeah, they don't know either. It's just something they cooked up to make it work.
I mean, the rate
Okay.
thing makes sense because it's basically you're looking at the dynamic.
Exactly.
But
So
the
like
other
that's.
one, you're not looking really at that.
Silly, not only that, right? Here, this harmonic rule, right? It's like inverse of the tube diameters. Okay, but this other one is like a linear sum with different weight factors. So like, I don't think anybody knows where that comes from.
Well, then, I mean, if you look at it the other way, like the tube diameter, it's an inverse of the tube diameter that's giving you the rate. Not the
Yeah,
tube diameter.
Exactly. Yeah.
In
That's
that
not.
case, it'd still be a rate law.
Yes.
So,
Yeah, that's a good way of looking at it. I completely agree.
so what does the inverse of the tube diameter mean? It's kind of a question.
Uh,
In terms of the rate, you know? Like the tube diameter, you can kind of see, I guess, how it relates to.
no. Basically, right. See, for instance, right, if the so if we think of the inverse of the tube diameter, so like thinner tubes will be more significant, right? Which means they have a bigger effect on the like on this average when compared to a much thicker tube diameter. Basically, the more it is constrained, the more effect it has.
Yeah. I like the rate idea.
All right, all right, run with it then. Yeah, whatever works. So,
Any other questions?
Yeah, please.
In your simulation, these are actually the points.
no, they're not points. They have a volume.
They have volume.
Yes, yes. I didn't go into the details. Like there is Leonard-Jones, purely repulsive Leonard-Jones potential between adjacent beads. Okay, so they cannot easily overlap. So that is why to do the primitive path analysis, I have to turn off that repulsive interaction. And then like there is a spring, right? Because it's a polymer. And the spring just pulls everything together. But the Leonard-Jones potential between different chains is still operative. So chains cannot cross.
But, okay, so then it's kind of in theory. But
Yes.
Then, but in your movie, you showed some lines connecting all these things. So how did you?
I mean, it's just visualizing, man. I just like connect the center of mass of all of them and I can show you lines.
It's through a software.
Okay, so I think you're talking about what this? No, that's probably earlier. Like, are you talking about this one?
Yeah, something.
Yeah, so like this one, right? These simulations are done using a software called Octa. Which was developed using during the DOI project, and all the molecular dynamic simulations in this was done using the Cognac part of Octa. So like the Octa has like many different software under one bundle, and each software has a food name. Okay. I mean, so there is sushi and pasta and cognac. So cognac does molecular dynamics. Sushi does self-consistent field calculations, and pasta does like coarse-grained slip link models, etc. Okay, so like, don't ask me why. Like, Yeah, but that's what they do. So like, I collaborate with the guy who is one of the developers of Opta. Yeah, this is from that. But like, this stuff is not from that. Like this is this is actually done using POV. Which is open source software. Okay, POV Ray. Okay, a point of view ray tracing program. So like that you can just search on the internet and you can find it. Yeah, but like, this needs some coding, so it's not just you can't just use the GUI. You need to know how to code to be able to do this.
Thank you.
Yeah.
I don't know if there's any questions about his career. When he started here, started in India, but kind of came here.
Yeah, I did my PhD here, of course, in his lab. So
Into postdoc. I mean, so when did you get a postdoc at Mike's?
I applied.
Oh. That's a negative postdoc.
Yep. Well, you wrote a recommendation letter too, but I don't know if you remember or not. So basically during my PhD, of course, I worked on scattering experiments because I was in Greg's lab, but I wanted to learn my molecular simulations. So I was actually quite torn. I also like attended an interview at ESRF in Grenoble, France. I got that position and I got this too. So I was quite torn between the two. Finally, I decided, okay, I want to learn something new. And yeah, like learning something new, the first year was a challenge. Okay, so yeah, because here our lab used only Macintoshes, and all the fitting I did was use like in Igor Pro. So like what little coding I did was Igor Pro, but there you go, and then you have to use Linux and C, and so they just dump you in that. And then I learned Perl to do data analysis, though I don't use Perl anymore. I use Python mostly. Right. So the first year was a challenge, but the second ultimately it turned out okay, I think. So yeah, that's how I went to mines.
I mean, it's the top place in the world, I think.
Yeah, for molecular simulation. That's one thing. So if you want to learn something, go to the place where the action is. I mean, I actually looked through the good places where you can learn molecular simulation. So
It's like maybe the second, maybe first. Or
no, Leeds was actually like I wanted to learn more about theory. Actually analytical theory, etc. So like Tom McLeish was heading the group there, and he was a leading figure in polymer dynamics. I think in 2002 or something, he had like written this really good review which summarized entanglement, entangled polymer dynamics. And like right when I was wrapping up in mines, I heard that there was a position opening up in Leeds. So once again, I applied, and they were actually very interested in this work. So that's where,
You teach in Japanese now?
Yeah.
So you learned fluent Japanese?
I mean, I wouldn't go as far as saying fluent, but I've learned some Japanese, at least enough to be able to.
Swear at people.
Yeah.
Yep.
Yeah, but then they'll probably just like swear right back at me. So plus their vocabulary will be better. All right, so like, I probably wouldn't understand half of what they used to swear at me. So
So anyway, thanks for coming.
okay, yeah, thank you all very much.
Anyone wants to talk about now?
Basically, I'll be here today and tomorrow. So if anybody wants to chat. Greg, shall I end this session?
This guy's doing DFT. Actually, now you're doing like the dynamic.